First of all, thank you very much for allowing me to spend some time with you this morning. I think I have about 20 minutes, and then I am happy to do a little Q&A, and then we need to get on with the program. I'm going to tell you a little bit about where we are in the development of a capability for interplanetary communication in support of both manned and robotic space exploration. I want to first acknowledge Adrian Hook, who passed away a couple of years ago, but he was very much instrumental in the development of the interplanetary protocols. He worked on the Viking mission, by the way. He was at JPL in 1976, and maybe a little before that. And so he was really the spark plug that got us going. Back about 1997, you'll remember the Pathfinder mission landed on Mars. It was one of the first successful Mars missions after several failures subsequent to the Viking mission. And in the course of that exploration, my colleagues at JPL, where I serve as a visiting scientist, and I were talking about what we might be doing then in anticipation of what might be needed 25 years hence. And in the course of our discussions, we thought perhaps we should do something more than just point-to-point radio links for space communication, because there are a variety of configurations of missions in which the devices would not necessarily have a direct-to-Earth path for communication. Well, as luck would have it, not very much longer after the successful Pathfinder mission, we launched the rovers in 2004. And prior to that, we had orbiters that were mapping the surface of the planet to figure out where the rovers should go. Some of you will know that the original plan for the rover mission was that the rovers would transmit data directly back to Earth on a path that would go through the Deep Space Network, those big 70-meter dishes. And for a variety of reasons, that did not work out well. The original plan was a 28 kilobit channel. And of course, the scientists were not happy about that. As it happened, there were some problems with the radios, and the end result was that they were going to have to reduce the duty cycle of the radios to avoid overheating and damaging either the radios or the other components on board the rover spacecraft. But one of the engineers at JPL pointed out that there were X-band radios available on both the orbiter and the ground-based rover, and that they could communicate with each other at 128 kilobits a second because they were closer together, and the signal-to-noise ratio was better. However, you couldn't use the X-band radio to get all the way back to Earth. So they reprogrammed the software on board the rover and the orbiting spacecraft so that you could forward data up from the rover and hold on to it in the orbiter until the orbiter got to the right place in its orbit to transmit data back to Earth. And since the orbiter was out of the atmosphere and had bigger solar power antennas, solar power for the antennas, it was able to transmit data back at 128 kilobits a second. So the consequence of the store and forward design is that more data came back at higher speed. So this was a perfect example of why even simple networking can be valuable. And I'm sure you all know that the internet is a store and forward network. That's packet switching, and that's how that works, and that's how this works. And subsequently, a number of other missions have gone to Mars successfully. The Phoenix mission in 2008, which was at the North Pole, and again, we used store and forward return for the data, and similarly, the Mars Science Laboratory. So we have a working demonstration that this technology is useful for scientific purposes. Just to give you a flavor of what we were going through way back in 1998, our first thought was, why don't we just use TCP/IP? It works okay for the internet. It works on Earth. It ought to work on Mars. And as we thought our way through that, we concluded, yes, it would presumably work okay on Mars, but between Mars and Earth, it might not work so well. There are a couple of reasons for this. One of them is that the distances between Earth and Mars are literally astronomical, and they vary from 35 million to 235 million miles. The radio delay is 3.5 minutes to 20 minutes one way, and of course double that round trip time. So the TCP protocols were not designed for 40-minute round trip time, to be quite honest. In flow control, for example, is very simple. You tell the other guy to stop when you run out of room, and if it takes 20 minutes for the transmitter to hear that you said stop, you have a problem because all the data is coming back in that interim period. So that there was this other problem called planetary motion. The planets are rotating, and we don't know how to stop that. So if you happen to be on one side of the planet and it rotates, so you can't talk to the device that's on the surface until it comes back around. Same problem with some of the orbiters. So we have variable delay and disruption, and in the end we concluded we had to develop a new suite of protocols that would accommodate both variable delay and disruption. So we also noted that even in terrestrial applications, especially in military conditions, tactical conditions, you get jamming, you get a lot of other interference or radio shadow and so on. And so the same mechanisms that make the delay and disruption tolerant networking work well for the interplanetary missions will also help in tactical military communications. We went to DARPA, the Defense Advanced Research Projects Agency, which funded the design, and said, we think you should try this out. We did. We ran tests of tactical communications using TCP/IP and using the bundle protocol, which is the DTN implementation. And the result was that we got 3 times more data through the bundle-based protocol. There's no magic here. The TCP system relies on end-to-end communication in relatively real time. The bundle protocol assumes there will be delay and disruption, and so we store data at intermediate nodes until a link comes up and is available for transmission. So we're doing something that we couldn't do in the internet design because the internet was designed in 1973 when memory was very expensive and it made no sense to store information in the network. In 2015, memory is cheap and it makes perfectly good sense to store data in intermediate nodes until communication links become available. And that's how you manage to get more data through because you hop it along as the links become available. So without going into a great deal of detail, because I'm sure most of you are not interested in diving too deep into the protocol design, but there are some other interesting things that make it very different from the internet environment. All of you know what domain names are, and you know that you type a domain name and something happens and then web pages come up. Well, the something that happens is a mapping of a domain name into an internet protocol address. These are numerical addresses that identify the physical connection of a device on the internet. In the case of, imagine that you have a device on Mars that's trying to communicate with something on Earth, and you generate the domain name, and now you have to do a lookup on the domain name system, which is mostly on Earth. Okay, so first problem is you have to transmit the query, then you have to get the data back. You don't know how long it's going to take the query to get there, especially if it's hopping through several intermediate nodes and there might be some disruption. And then by the time you get the data back, what happens if the device that's on Earth is mobile? The IP address that you get back may be wrong because the device is moved and is connected to some other place in the internet. So trying to use standard internet protocols for this kind of communication did not look very attractive at all. So we had to develop a completely different architecture with sort of 2 layers of identifiers, one of them to figure out which planet you're trying to get to, and then after you get there, then you figure out where is it on the planet that you're supposed to do the lookup. So you do the resolution wait, it's called delayed binding, and that's the bundle protocol architecture. The other thing is that network management is very different in this environment. In the internet world, which again is mostly low delay and generally high bandwidth these days, if you want to know if a node is up and awake, you send, literally, it's a message called ping, which says, please echo this packet back. Well, the problem with running network management that way on Mars or even further out to the more distant planets is that it takes forever to find out if anything is up. And by the time you get a signal back, if you get one, you don't know what the real state of the device is because it might be dead again. So this network management architecture is very different. Autonomy becomes a very key part of architectural thinking, which is true, as you know, for the rovers as well, because you can't literally steer them because of the round-trip time delay and the dynamics of the planetary rotation. And so you have to send information to the destination to tell it what to do, and then it has to do it more or less autonomously. So these kinds of concepts force you to rethink a lot of the architectural design of the system. Now, I have some views about Mars missions, and they may not necessarily coincide with everybody's, but I thought, given this opportunity, I would at least share them, and you'll have a few minutes to rebut if you feel the need. One thing I think is really important is continuing a vigorous robotic reconnaissance program for several reasons, one of which is to understand what are the conditions out there, what are we likely to find if we send people there. And I'm particularly concerned about what happens between Earth and Mars for humans being transported. What radiation environment will they experience? What other kinds of things might they encounter that we should know about before we send them there? The second thing, of course, is a very exciting idea, is that we found water on Mars, maybe not as much as we would like, but the possibility of doing in situ fuel production, production of oxygen and the like is extremely attractive if we can do that. And there's no reason why we couldn't send a mission to perform that function and verify that, in fact, it's feasible. Of course, we have to know where to send that mission in order to find enough water to make it worthwhile. Another problem is it takes a long time to get to Mars with the current spacecraft we have available. And so having better propulsion systems that could reduce the delay would also reduce the risk for people who are en route if we have a manned mission. I would certainly like to be able to demonstrate that we have a resupply capability to Mars before we send anybody there. And that, too, is the kind of mission that you could do in a robotic fashion. And so I would be interested in seeing that be part of the program plan. Finally, I think that making sure that we have high-resolution orbiters available, possibly to replace the ones that are currently there with even better optics, would be very valuable. And I'd also like to make sure that we have good communications capability. Now, one thing I do have to say, and every one of you must have experienced this, you watch these science fiction movies and they're out on Saturn in orbit and suddenly there's a problem and there's this real-time communication between Saturn and, you know, it's all baloney. But the movie would be boring if you had to actually wait for all that time. But the fact of the matter is that we cannot and should not mistake that the communications that we have available is going to be delayed. And so it's not going to be the kind of interaction that, you know, we wish we could do with sublight or whatever it is, subspace communications from Star Trek. So we have to really be thinking about what it's going to be like with the communication delay to interact with people who are sent on missions like that. And finally, of course, when they get there, we hope they have a safe place to stay. And so it would be nice to have some verification that a habitat can be landed safely on Mars, and we could demonstrate that it maintains an environment that would be suitable for human habitation. So my view is that a lot of these things should be going on, and they probably conflict to some extent with a 10-year profile for getting humans to Mars. But my view is that I would prefer to delay getting people to Mars if it turns out that we can do a safer job of delivering them there with all of these considerations taken into account. So let me just mention that our hope with the interplanetary design is that we can standardize the protocols so they can be used by anyone. And we're very far along in that process. There's something called the Consultative Committee for Space Data Systems. Its members are all of the spacefaring nations, US, Japan, the European countries, Russia, and so on, China. And they have already agreed on standards for interplanetary communication based on the bundle protocol design. So we're well on our way to standardizing this. There's open source software available at SourceForge. And if you had an interest in playing with these protocols, you could download them from SourceForge and run them on any of the existing operating systems. They run on Linux, it'll run on Android, it'll run on well, I don't think we have it for OS X, to be honest, and I'm not so sure about Windows. But we do have it running on the operating systems that are typically used for space missions. The protocols are in operation now. The prototypes are in operation between Earth and Mars, relaying data back through the orbiters. We have the full bundle protocol on the International Space Station. Last year, we tested real-time interaction between the astronauts on the International Space Station and a small robotic device in Germany to do real-time control, which makes sense because they're only a couple hundred miles away. You could imagine that being a kind of emulation of a mission where somebody is in orbit around Mars controlling devices directly. So I think that over time, what we hope will happen is that the spacefaring nations will launch missions for scientific purposes and use these protocols either during those missions or after the mission is complete to turn that spacecraft into a relay so that we literally grow an interplanetary backbone mission by mission. So over the course of the next several decades, we may well see an interplanetary backbone come into being. So it's not like we're saying that we should go build this giant interplanetary backbone and hope that somebody will come. That's not the model. The idea is that we literally grow it as the need evolves. And so I think it's quite feasible for that to happen. And I realize that I'm getting close to running out of time. I did want to mention one other thing, and that's a mission that the Defense Advanced Research Projects Agency funded a study for. This is the 100-year spaceship, so some of you probably know about it and may even be involved in it. I'm very excited about this study. I've been participating with ICARA's Interstellar, which is based in the UK, which is participating in this design effort. There are several problems trying to get to Alpha Centauri. The obvious one is that current propulsion systems would take us 65 or 70,000 years to get there. That's pretty long, even for a DARPA project. So, one thing that we're very interested in is propulsion systems that could get us up to a significant fraction of the speed of light. So that by the 50-year mark, we're halfway there. And then, of course, we have to slow down at that point, because if we don't, we'll go blasting through the Alpha Centauri system and get one picture. So that would be disappointing. So propulsion is one thing. Ion engines are almost certainly the most likely candidate for this kind of mission. The second problem is navigation. It's a typical thing when we do planetary missions in our solar system that you get partway through the mission and you do mid-course corrections. Imagine if you have a spacecraft that's a light year away on its way to Alpha Centauri, which is 4.3 light years distant, and you have to tell it to do something. Well, it takes a year to tell it, and then it takes another year to find out what happened. And so this is not a very interactive environment. We'll have to use autonomous navigation. I think by good fortune, most of our information about stars in the nearby neighborhood, within 10 or 20 light years, we have a pretty good idea of what their planetary, or what their motion is, so that we could use onboard instruments for navigating. Because even over a 4 light year distance, some of these major star signals stars are not going to shift in their apparent location. And then there's communication, which is the part I'm most interested in. The question is, how do you generate a signal that you could detect from 4 light years away? This is a non-trivial thing to do. So the thing that's come to mind for me right now is femtosecond or attosecond lasers, where you can compress the signal down to a very, very brief pulse. If you put a lot of power into a brief pulse, you get a big spike. And that signal might be detectable from 4 light years away, assuming you aim the laser in the right direction. Even though it's a laser, the beam is going to spread over 4 light years. And so now you know why I need an interplanetary backbone, because I need a synthetic aperture receiver to integrate the signal back that's coming from Alpha Centauri. One of the physicists suggests another alternative, which is to put a spacecraft at 550 astronomical units away from the sun, which is roughly where the focal plane of the sun's gravity field is, and then use the focal plane, use the gravity of the sun in order to capture the optical signal coming from Alpha Centauri. That would actually be a good experiment, because if you have what you believe is a propulsion system that's worthy of an interstellar mission, you should send it out to 550 AU and see whether or not we can do this kind of focal plane integration. So that's the latest update on interstellar and interplanetary communication. I'll stop because I've already run out of time. Thank you for your time. Good luck with the rest of the meeting. I'm sorry I can't stay for all of it, and I'm happy to try to answer questions if you have them. So, Lars.
Buzz Landser from Mars One.
Wait, I'll tell you what, we should, is there a, You could talk into my lapel, but
Seems a bit cozy.
yeah, that's better.
I was very interested when you said that it would be the interplanetary internet would be sharing between all the nations the bandwidth. Would the owner of the node get advantage? How do you say that? Would go before the other data that is coming, or is there really?
So we have a big priority.
First come, first serve.
This is a big argument. Well, what one would hope is that scientists would at least agree that they would share the bandwidth. One big problem is how much capacity is there, in fact. So we have prioritization capability in the protocol design, actually. We also have a mechanism that lets you say, this packet is so old, it's not worth forwarding anymore. And there could be situations where that could happen, and so we would discard the data. The other thing I didn't say is that, and you didn't ask, but I'll tell you anyway, we were very worried about security in a system like this. The headline I did not want was 15-year-old takes over MarsNet. Bad idea. So we introduced at the beginning of this design a strong authentication, cryptographic authentication mechanism. So each of the nodes could verify that the node that they're talking to is one that they're supposed to service and interact with. And we also encrypted the traffic just for safety's sake. If it turned out that we had astronauts communicating, presumably they'd want some privacy. So the protocol has designed for both strong authentication and confidentiality. Okay, other questions? We only have a couple of minutes left, I think. Yes, sir. We have a microphone. There. Well, it's actually over here.
Gil Levin. With all the nations becoming spacefaring, how are you going to coordinate so that they all have the proper band and don't interfere with each other?
Okay, that's it. Well, this is a classic problem. In fact, we ran into this problem on Mars. A number of countries were launching Mars missions, and there was this, and also to the moon, and there was a big issue about that. I went to the FCC asking them whether or not they were prepared to deal with interplanetary frequency applications. In fact, the CCSDS, our organization, has the responsibility for helping to sort that out. Even if they're in the same radio band, though, these protocols, because they're packet switched, in theory will allow concurrent interactions, especially if we use what spread spectrum communications, which will allow you to separate two signals that are being transmitted in the same frequency band. It's a classic design. The military has been using it since about 1973 or so. So that's how we hope people will be cooperative about this. Okay, we have one more, I think. I'll let you decide whether I have time for this. I know you're trying to get. Yes, this nice lady over here. We'll get you over there. Okay, so this is 1 and 2.
Good morning, Dr. Cerf.
Good morning.
Question for you. I'm wondering what the chances are that Google may be interested in collaborating with the Mars One mission when it comes to developing interplanetary communication systems.
Of course.
Wow, could we get that in
So
writing?
there he is. He's right there. We've already exchanged cards.
Have we? Fantastic news.
And don't you find it a little odd that it's the 21st century and we're handing each other little pieces of cardboard?
Well,
but anyway.
I'll tell you why that's so meaningful to me. I'm here with a number of my friends, and we're all part of the Mars 100, and
Great.
we're very interested in finding out more about the possibilities that lay ahead.
Absolutely.
Thank you.
So we've made contact. This nice lady over here, no, I guess that's probably not a good idea. This is like the hot dog in the baseball game, right? Yeah. Yes, ma'am.
Once you get this system into place, what do you estimate the initial time lag would be in the solar system, especially towards Mars?
I'm sorry, I did not hear all of that. Say.
I said, once you get the system into place, what do you think will be the initial time lag
Oh,
in the solar system with Mars?
So, actually, to say after, the way you asked the question sort of implied that nothing works until we have everything in place, and that's not the case. So this system will simply grow piece by piece, the same way the internet did. It's a very organic kind of architecture. So the answer right now is that we have capacity at the moment to support a fair amount of communication. It's still fairly low data rate stuff, but there is some really exciting optical communication results that have been demonstrated recently. I don't know if anyone has reported that to you from NASA, but they did a 600 megabit per second transmission bounced to Earth, from Earth to the moon and back. And so we are already testing the interplanetary protocols at much higher data rates than are classically available. So capacity may not be a problem after we get optical capability in place. But the whole system doesn't have to be there to support specific missions, just enough of it in the right places. So the good news is, if you were looking for timelines, I don't think I know how to do that because it's dependent on the Congress deciding to spend money. You're hopping up and down, yes?
Will you be including a GPS network of these data satellites going around Mars so you could have some sort of rudimentary GPS on Mars?
Theoretically, you could do that. I hadn't considered incorporating GPS into the architecture. It wouldn't be GPS anyway, it would be APS or something, but anyway. I don't see why we couldn't do that. Now, I hope all of you know that our terrestrial communication systems are very dependent on GPS, not for the geographics, but for the time signal, because time is very important, especially in LTE, the latest version of mobile. So the answer is it's not a bad idea. But I don't have any control over that particular part. I'm focused on communications. I think we got to wrap up. But thank you again. I appreciate your time.